Hi and welcome. I'm trying to learn particle physics, today quarks, and after we've done that we're going to do stretching, and if you participate in the stretching then it's werdet ihr auch das. This is part 4 or 5 of quarks or so. The difference between their masses, between neutrons and protons, is about 0.1%. But boy does it matter. The neutrons extra mass means neutrons decay into protons via beta decay, not the other way around. Our current best guess is that the proton's half-life, a measure of its stability over time, is at least 10 to the 32th years. Given that the universe only has a 10 to the 10th or so years behind it, that is a convoluted way of saying no one has ever seen a proton decay. What I'm saying is that neutron can decay into the proton because it is heavier it has. Neutron has in it the parts to build an electron and a proton. The neutron is therefore neutral. A proton cannot become a neutron because it does not have the electrons in it. If it wants, it's going to say in a moment, it needs the electron. The persistency of protons means they can team up with negatively charged electrons to form robust, structured, electrically neutral atoms. So a proton can take an electron and then become a neutron. A neutron by itself can, through beta decay, become a proton and splitting off thereby that excess electron. The persistency of protons means they can team up with negatively charged electrons to form robust, structured, electrically neutral atoms, rather than the world being a featureless neutron glob I understand. The protons can team up together with the electrons and become an atom, and therefore this atom is then electrically neutral, because it has now so much protons and so much electrons. And so the world is not a featureless neutron glob. But it is atoms because protons can team up together with electrons and coming together neutron, one proton, one electron. The exact amount of a neutron's excess baggage matters too. So 0.1% is the neutron heavier than a proton. So there is some excess baggage. The simplest atom is hydrogen. Hydrogen was made in the Big Bang before becoming fuel for nuclear fusion in the first stars, which forged most of our chemical elements. The hydrogen is the first element, the one, and it is the fuel running in the stars, in the stars which makes the star burn or something, and where the other chemical elements were done. Had the proton-neutron mass difference been just a little bigger, adding more neutrons to make more complex elements would have encountered energy barriers that were difficult or impossible to overcome, says Frank Wilczek at the Massachusetts Institute of Technology. Okay, let's read it again. Had the proton-neutron mass difference been just a little bigger, it is 0.1%. Adding more neutrons to make more complex elements would have encountered energy barriers that were difficult. So, adding more neutrons. But is it not the protons adding up together with the electrons? Whatever, they're saying is this important. It wouldn't have happened because the energy barrier would be too big if it would be the difference bigger. The universe would be stuck at hydrogen. There would be just one element, hydrogen. But because the protons and the neutrons are so little in their mass difference, it is possible that the energy jump is being made and other elements can be created. But had the mass difference been subtly less, hydrogen would have spontaneously changed to the more inert, innocuous helium. I'm not sure right now which one is the first element, hydrogen or helium. Helium before stars could form. So if it would be less the difference than 0.1%, then the hydrogen would have just become the helium. And the cosmos would have been an equally limp disappointment. Narrow the gap further, and hydrogen atoms would have transformed via a process called inverse beta decay into neutrons. And another sort of neutral particle, the neutrino. Bingo, no atoms whatsoever. Let's read about it again here. Inverse beta decay into neutrons. So atoms would have become neutrons themselves, and the neutrino. I don't really know what we want to explain now with all what I mean, but we're basically saying if the difference would be somehow different, more little, when it would not have... Right now the difference is wide, exactly 0.1%, but it is possible through a nuclear fusion reaction in a star to create a new chemical element. If the difference would be lower, then spontaneously a new element would have been created. And not just slowly, over time by fueling, but just hydrogen had just to become helium. And if it would be even littler, but the difference in neutrons and protons would be exactly the same mass, then then they would not have become into our chemical elements with other atoms or whatever, they had jumped to become other particles. They had not become neutrons or protons as they should when they're decaying. They had done inverse beta decay. So these, whatever now, these neutrons would have not formed protons and electrons. These neutrons would just spontaneously by themselves, if the difference would be so little, become neutrinos, so another type of particles. And therefore, no atoms would exist at all because neutrinos would exist or something like that. All of it leads to an unavoidable conclusion about the proton and neutron masses. Without these numbers, people wouldn't exist, says Zoltan Fodor at the University of Jupiter, Germany. So what I basically want to say, it is important that there seem pretty exactly 0.1% difference in the mass of protons and neutrons. Otherwise, if it would be more, it would not happen that other chemical elements would come. If it would be less, they would do it themselves, just new elements, and that would not make sense. And if it would be even less, they would not form to other elements, but into other types of particles, not into other atoms, not into other protons and electrons or whatever. They would form into neutrinos or whatever, other type of particles, not even atoms at all. Working out where they come from is another matter. Down quarks are slightly heavier than up quarks. And don't expect the neutrons to down quarks, but don't expect the neutrons to down quarks versus the protons want to explain the neutrons slither with extra mass. Whatever, they're basically riddling around why these quarks have different mass. Both quarks' masses are tiny. It is hard to tell exactly how tiny, since quarks are never seen singly, but the up quark has a mass of something like 2.2 MeV, or something. Mega electrovolt. A sliver under 4,000 billionths of kilogram. And the down quark may be double that. Okay, what was I saying here? The up quark has a mass of something like 4,000 billionth of a kilogram, and the down quark will double it. And we cannot find quarks themselves. We cannot find quarks singly. We said we cannot separate them, always together with someone else. And we're guessing that one quark, with up quark, has 4,000 billionth of a kilogram. So I guess something very, very little of a kilogram. That makes sense. It is very little. This is a very tiny thing in an atom, so it must be very, very light. And the down quark is double of it, heavy. On top of it, half. Whatever. That is just a tiny fraction of the total proton-neutron mass. We're saying the up quark has a mass of something like 2.2 MeV. The proton has 939, and the 938, and the neutron has also 939. So it has a 500th of the electron mass, of proton mass. The electron is less. They said it somewhere else. The electron is also way less than a proton and neutron. Proton and neutron are way heavier than electrons. Now, like our fundamental part, no, we're not going to read on. But I have some one little thing which I want to have as a video. We're having the weight of neutrons. Let's read the sentence again. Take a simple question as to the difference between protons and neutrons. For example, obviously protons have a positive electrical charge, whereas neutrons are neutral. But we also have ever so slightly variant masses. In the units that particle physicists use, the neutron weighs in at 939.6 mega electrovolts and the proton 939.3 mega electrovolts. And they are 1,800 times heavier than an electron, basically. I want to say these two things. These four things are not those numbers. 939.6 is the neutron. 939.6 is the neutron, 938.3 the proton. Difference is 0.14, And we're still above 1,800 times heavier than an electron. This is the start of the curve again. 39.6 and 39.6 and 338.3. That will be according to Richard Webb's particle physics 939.6 and 938.3. First thing we'll do. A neutron weighs 939.6 megaelectrovolts and a proton 939.3 megaelectrovolts. That is a difference of 0.14% is the proton lighter than the neutron. But they're both still more than 1,800 times heavier than an electron. That is according to Richard Webb's Particle Physics Understanding Reality's Building Blocks book, page 38. I don't know if I said what I said, or this, but I can't remember what I said. I'm going to stop the camera. Whatever, I'm going to write what's right, but I think it was right. Now, that was the particle physics part. If you were here for particle physics, you can go directly to the next part of particle physics. We will do no stretching. If you didn't participate in the stretching, then it's better down risk. Next, standing shoulder by the part a bit more, the breathing in and lifting out. And breathe out to one side. Breathe in the middle. Out to the other side. Okay. Out in the middle of the arms down. Breathe again in. And out one hand slides down the leg, and the other shoulder stays down. Breathe again in. Out one up. Breathe in up with the cage. Out into the middle. Again in. Out one hand slides down the leg, the other shoulder stays down. Again in. Out the other. Breathe in. Head feet in together. Breathe in, lift the arms up. And breathe out one head down. Breathe in and reach. Out hand up. Again in and down. Breathe out. And breathe in and reach. Out my hand up and the arms down and legs wide apart. What was doing? Not at the right apart. A bit more shoulder wide apart. Do shoulder circuits. Short. And no fall. And now breathe in the shoulders up. Out and go fall down. In and up. Out and down. Breathe in the arms up. And now breathe. Always with one arm high up. Pretend to take in everything higher than upper branch. Momentum. Lift it out. And over to the shifter. Legs wide apart. Arms up to deep breathe in. And out. We are shifting over to one side. In. Out over to the other side. Again in. And we lean onto our knees. We're doing the buffalo fighting its hangover. We're breathing in. And out we bring our shoulder front. In the back. Out the other front. In the back. Out the front. And out we're hanging down the Niagara Falls. Breathe in. And out go to one leg. Breathe in. Then go out to the other leg. Breathe in. Out to the other. And now close my feet and we're doing the Santo Angelo. Just keep hanging down. Breathing in. And out. Again. And now you can slowly push on back up. I can get the top of the back with the shoulder. Legs wide apart. Breathing in, go down. And breathe out. Again in. Out. Out. Breathe in, close the legs. And breathe again out. Now a bit force stretching. I thank you very much and enjoy the next time.